Okay, implicit differentiation. So all the derivatives we've seen so far are functions. For example, we might have y equals 2x cubed minus 5x plus 1, and we've taken the derivative with respect to a certain variable. In this case, we take maybe the variable x, and we can use the correct laws and get our derivative. However, it is possible to take derivatives of relations or to take derivatives of variables not just x, and that's what we'll learn today. So let's take a look at this through an example. Suppose we have the relation 2x squared minus 3y squared plus 5y minus 6x is equal to 0, and we want to take the derivative of this with respect to x like we've been doing in the past. And the derivative for this is still, what we're looking for is what y prime is worth. But I've got this complicated relation where the y's and the x's are all mixed together. That's okay. We can just take this apart slowly and apply this implicit differentiation to do that. So let's start by just stating what we want to do, which is take the derivative of everything. And by that I mean we're taking the derivative with respect to x of each side of our equation. And that means I can take the derivative and I can apply it to each part. So let's do that next. Now, some of these are easier to take the derivative than others. For instance, the first term, we know how to do this using the power rule and get 4x. And let's skip these ones for a while. We also know this fourth term has a derivative of 6 and that the right-hand side has a derivative of 0. These other two are a little bit trickier. When you take the derivative with respect to x and you have a variable that isn't x, you need to account for that. And the way that you do that is you take the derivative like you would normally. So this is 6y, drop the power by 1, but then we need to add in the fact that we've taken the derivative of y with respect to x. We don't know what that is, so we need to write it in, that we still have a derivative with respect to x. A similar thing happens on the third term. This is considered to be a product, so we use the product rule. I'm going to get two parts in here. The first part is the derivative of 5x, which is 5, times the other part, which is y, and then the second part of the product is 5x times the derivative of y, and the derivative of y is this dy dx, or y prime. This is the exact same thing as finding y prime. So now I've got an equation that looks like 6y, you can use y prime or dy dx, plus 5y plus 5x, y prime minus 6 is equal to 0. And our goal now is to solve for y prime. The easiest way to do that is to put all the y primes on one side, put everything else to the other side. So I have 5xy prime and 6y prime is equal to, moving everything to the other side, I get minus 4x minus 5y plus 6. Then I factor out a y prime, leaving over 5x plus 6y, and divide everything by, in this case, 5x plus 6y. Leaving me with my derivative of minus 4x minus 5y plus 6, all getting divided by 5x plus 6y. So we're going to, for this example, find the point-slope equation of the tangent line at the point given, 1, 2, on the relation y cubed plus 2xy equals x cubed minus x squared minus 12. Notice that this is a relation. Let's go take a look at what this looks like with a graph, so I'll use some technology to do that. Okay, here's the graph. If I zoom in a little bit on this graph, I can see that the point where x is 1 and y is 2 is about here. Notice this is a relation that fails the vertical line test over on the left-hand side there. And the slope looks like it's kind of going this way, which would be negative. So hopefully when we calculate our tangent line, we end up with a y value in here somewhere and a negative slope. So let's go ahead and do that algebraically. Okay, and to actually find the point slope equation, I'm going to need the point, and I have that 1, 2, and I'm going to need the slope. Now I've made a little mistake. This is actually a positive 12 on the end here, and the graph was actually a positive 12 that I showed you with the technology. Let's go ahead and take the derivative of this with respect to x and solve for the slope, which is y prime. So taking the derivative of the first part, I get 3y squared, and then the derivative of x with respect derivative of y with respect to x, which is y prime. Product rule, so the derivative of 2x, which is 2 times y, plus the first part, which is 2x, times the derivative of the second part, which is y prime. And continuing along, I get slightly easier stuff on the right-hand side. Solving for y prime means move all the terms that don't have y prime to the other side. So I get 3y squared y prime, 2x y prime is equal to 3x squared minus 2x minus 2y. Factoring out a y prime gives me this. And then dividing everything by 3y squared plus 2x gives me 3x squared minus 2x minus 2y, all being divided by 3y squared plus 2x. Now that's the slope. If I want to know the slope at the point 1, 2, I need to substitute in the values for x is 1 and y is 2. So if I do that, I get 3 times 1 squared minus 2 times 1 minus 2 times 2, all divided by 3 times 2 squared plus 2 times 1. And calculating that, I get minus 3 over 14. So I can now use point slope to state my solution, which is y minus 2 is equal to the slope and x minus 1.